Very good. Good morning, everyone. Thank you for coming out this morning to the Carnegie Endowment for International Peace. We're very appreciative of you taking the time out of what are inevitably busy days to come and listen to some speakers that we're all very, very excited to hear from. The topic of today's discussion is a diverse one. It's climate change, air quality, and how these two mega forces of the 21st century are expected to shape various different countries and indeed the global energy innovation agenda. 2015 was a watermark year with respect to the mounting challenge of climate change. Last month was rated as the warmest on record by both NASA and the National Oceanographic and Atmospheric Administration, which released their data recently. And in the temperature annals kept by NOAA, it was marked as the 13 record warmest month in a row. We are almost assuredly on pace for yet another record warm year. But so too is the history and the geography of local pollution challenges evolving. India is now grappling with an air pollution problem that is more severe than that of China. The country's expanse along the Gangetic Plain is draped with smog for much of the year. India accounts for 13 of the world's 20 most polluted cities in terms of particulate matter, according to the World Health Organization. And it is estimated that 660 million Indians are living in pollution that exceeds the country's national air quality standards, which themselves are less stringent even than countries such as China. By one estimate, simply meeting the country's own standards would extend average life expectancy by over 3 years immediately. Both India and China also have significant carbon emissions that, though much lower than the West in terms of per capita metrics, are nonetheless rising and rising rapidly. Emissions and energy intensity is already much higher in China, which aggressively pursued for the past several decades a strategy of industrialization in order to drive development. India's own development has been a bit more balanced, has had a larger share of services, but is now poised to change and dramatically restructure on the back of government priorities that have put manufacturing front and center, most saliently with the country's own Make in India initiative. The way that these two countries and others such as Indonesia, Brazil, Turkey, etc., that are fast followers on the upward ramp of economic development, but also of local and global pollution. The way that they develop their economies, the way that they develop their energy sectors in the years ahead matters greatly not only to their own citizens, but indeed to the world. The quality of future growth, even more so than the quantity, will then be determined by the technologies employed, the energy sources used, and the degree of harmful pollution, a byproduct of growth, that is mitigated. This, in turn, depends greatly upon the innovative capacity of each country and the global system as a whole, and the speed and efficacy with which technologies and lessons from one geography diffuse across borders to others. To discuss these challenges, the frameworks, tools, and lessons that are best suited to address them, we've assembled a very diverse panel of experts from academia, government, and civil society. We'll lead off with presentations on each of our two panels, from our two panelists serving on each, and we'll begin with a panel that will unpack a bit of the science underlying the air quality challenge, the climate challenge, and the ways in which they interact with one another. To lead this panel will be my colleague, Deborah Gordon, the director of the Energy and Climate Program here at the Carnegie Endowment. I'm an associate in that program and will be moderating the second panel. We'll lead off with a presentation from Daniel Horton, who's a climate scientist and the principal investigator of the Climate Change Research Group at Northwestern University. And that presentation will be followed by Seth Shonkoff, who's the executive director of the Energy Science and Policy Organization, PSE Healthy Energy, and he's located in Berkeley, California. We're very thankful to both Seth and Daniel for making the trip out to Washington, D.C. this morning. So without much further ado, let me hand it off to panel one. We look forward to a very vibrant discussion We hope you'll stay through as well to the second panel, which will take the scientific learnings, and discuss the energy innovation agenda for the way forward. Thank you very much.
Thank you, David. I'll just add to that it was at Paris where David and I were last December at the climate talks at COP21 that this had followed horrible pollution in Beijing, Delhi as well. All of these countries are assembled for climate change. And at some point, David and I looked at each other and wondered, especially when the island nations were coming on board, and there were a lot of local issues that were getting people to a global climate agenda conference finally. And we looked at each other and we said, where's the discussion on air pollution here? Because it seems so profound to the quality of life in these places. And then the begging question after that was, and what will climate and a warming climate mean to that air pollution? So that was really the impetus for having an event like this, because David and I just imagined that this probably will be part of the conversations at the COPs going forward to continually engage a lot of these emerging nations that are going to struggle with these issues, and probably the developed nations, the Western nations, that are going to struggle again with these issues because a warming climate changes a lot of the equilibrium of everything in the air. So with that, to kick off on the science, we'll start with Dan.
Thanks, Tim. Good morning, and thanks for having me. Thanks for coming out. Thanks, Debbie. So I look forward to learning a lot today. We're definitely a diverse group, and there's a lot of things that are going to be talked about that I don't have any expertise in. But I do know a little bit about climate. As a climate scientist, we kind of get a bad rap, or maybe accurate rap, that we always bring negativity to everywhere we go. And so I make a rule that wherever I go, I have to say at least one thing that's positive. That usually means I have to present someone else's work. So here's some paintings by Claude Monet. This is the Houses of Parliament series. These were painted around 1900 in London. There's a little over 100 of these paintings. They were all painted from the exact same place in London. And there's several people that believe that these paintings are actually in situ observations of the air quality at that period in time. There's scientists that have gone to found that bridge and looked at the sun angle and tried to figure out what the constituents of the air were during that time. It's really interesting work. It's not mine. But in terms of positives, this really bad air quality led to these beautiful paintings. So that's good. And secondly, if you've been to London lately, it doesn't necessarily look like this anymore. And so we know how to fix this problem. So in terms of the ingredients that go into causing a poor air quality event, there's primarily two things. And the first is the existence of pollutants. And so in this plot, we're just looking at some anthropogenic pollutants. And this is a plot from the EPA. This is just national, so US-based. And this is the distribution of total emissions by source. And the sources are down here along the bottom. And you can see that they are stationary fuel combustion, industrial and other processes, highway vehicles, and non-road mobile. And so these sources are all things that are related to our expected quality of life. And in some cases, things that we consider to be primary human rights. And so all of these processes down here along the bottom, they include the generation of electricity, the creation of consumer goods, transportation. All of these things are things that we expect to have here. And in developing nations, these things will become the expectation. And so these pollutants will remain an issue moving forward. Okay, the second component, or the second ingredient in poor air quality, is the weather conditions. And so when I say weather conditions, what I'm talking about are conditions that allow pollutants to accumulate and or form. And so this particular table is from a review by Arlene Fior et al. And on the left-hand side, we have the meteorological process. And And then in each of these columns, we have different relationships between those meteorological processes and how they will relate to the concentration of particular pollutants. And so in this first column is particulate matter, and in the right-hand column is ozone concentration. And the first thing, the broad takeaway from this plot, is that there's a complicated message here. All of these symbols depict different levels of our understanding. And so we can, if we're having a double positive, we're looking at consistently positive relationships between an increase in the process and an increase in the concentration of the pollutant. But you can see that not all of these are consistently positive. There's some weak. There's some places that there's some things that we don't know. And then on the ozone side of things, things vary on a spatial scale as well. There's background or baseline ozone levels, and then there's local to regional differences. And so because this is a climate change talk, we can add yet another level of uncertainty to this, and that is how these meteorological conditions will respond to climate change. And so this middle panel here talks about our level of confidence that warming climate will lead to an increase in these conditions. And just as an example here, we can look and see precipitation. We know very well that an increase in precipitation, or the frequency of precipitation, will lead to a decrease in the concentration of particulate matter that's in the sky due to the scavenging processes. But our confidence in the increase in the frequency of precipitation with regard to precipitation is very low. And that's due to modeling difficulties or just the noisiness of the baseline of precipitation. And so one of the things that we can do is look at this, kind of summarize this, this middle panel, and the IPCC report has done this for us. But if we look real quickly, we only see one area that we have high confidence. There's some mediums, but a lot of lows. And the statement that the AR5 report put out was that there is high confidence that the response of air quality to climate-driven changes is more uncertain than the response to emission-driven changes. So that statement, from a climate science perspective, suggests lots of research opportunities. So we'd like to increase the confidence in these predictions. So a couple of examples of this kind of research. First, you may have noticed that the variable temperature wasn't on the previous plot. But you probably associate temperature with ozone formation. However, on that panel, you can see that there's several temperature-related processes. And if we restrict our analysis to just things that are consistently positive or negative with regard to ozone, we can see that there's several positive and several negative. And so this is a complicated relationship in terms of temperature and ozone. And one of the methodologies that we use to try to figure out what's going to happen into the future is to model this. So we put this information into a model, and we can simulate it. And so this bottom plot is a model, is an amalgam of several different model ensembles. And this is the 2050 surface ozone relative to our present levels. And if we look at this, we have the 0 level here, indicating no change, and then the gray areas are negative, white areas are positive, and we break this up by region. And if we look first at the global region, we can see that from just a climate perspective, if we only look at the blue, climate change is expected to reduce on the global level the amount of ozone in the atmosphere. And this is a relationship that's due to the increase in humidity in the atmosphere, and with the presence of water vapor, photolysis removes ozone from the atmosphere. It's a sink. But if we look at the particular regions, we can see that there's a distribution of both positive and negative in many of these regions. And this distribution is due to a phenomenon where the photolysis that occurs in the presence of water vapor on the global scale doesn't necessarily occur in highly polluted areas. And so that the presence of water vapor in polluted areas actually leads to more ozone formation. And so there's a mixed signal here between the baseline and the regional signal of ozone pollution. Okay, a second meteorological example, and this one has a bit more of what I call a target-rich environment, and that's regional stagnation. You can see that stagnation, we have medium confidence in this, but in each case of both ozone and particulate matter, we see increasing concentrations, the double positive here, with increasing regional stagnation. And so this gives us an opportunity to look out into the future and look at the changes in regional stagnation or stagnation. And so this particular plot is a 90-member bias-corrected CMIP ensemble of opportunity. This is the late 21st century change in air stagnation days. And so here in the US, the National Climatic Data Center puts out something called the Air Stagnation Index. I've taken that index. This is an index that looks at when there's low winds aloft, low winds at the surface, and a lack of precipitation, and calls that a stagnation day on any particular grid cell. And I look at that both in the future and in the present, and I subtract them, and here's the changes into the future. And so the white here are areas where the change in the climate change signal doesn't rise above the noise. The gray are where 66% of our simulations have significant change, but they don't agree on the sign. And then finally, the red and the blue areas are where significant change occurs, and the sign in that change is consistent across the models. And so the first takeaway we can take is that changes in regional stagnation are diverse. There's red areas, there's blue areas. The areas where the signal rises above the noise are spread throughout the globe, and they happen to coincide with many areas that are industrialized, have high populations, and many regions have pre-existing air quality problems. So in particular, you're looking at the western US, over Mexico, and India and China. So we can take that information and take a step further and look at the exposure of this people's exposure to increasing stagnation. And this is a simple metric where we take the year 2000 population and multiply it by the robust stagnation occurrence change. We don't change the population. We don't make a projection about the population into the future. And we can look at this on a logarithmic scale and kind of tabulate these. So decreasing, it's a lighter green, and the darker green is increasing exposure. And from the left-hand column here, what we can say is that about 55% of the global population can expect an increase in stagnant conditions, while only 10% of the global population can expect a decrease. Approximately 50% of that increase is found in India, which is highly problematic. Okay, lastly, I wanted to talk about some emerging research. And this has to do with compound events. And so in this particular case, I want to talk about the meteorological conditions that cause extreme heat waves and extreme air pollution events. The meteorology between these two events is very similar. And typically, what happens is an upper level blocking pattern emerges. So kind of like a high pressure system at the surface. And so we have a couple anecdotal examples here. So this is the European heat wave in 2003 and the Russian heat wave in 2010. So in upper levels, we have this blocking pattern. Lower levels, we have extreme heat. And these meteorological conditions are very similar to what occurs in a stagnation event. And so these anecdotal examples, in the case of the European heat wave, resulted in 70,000 premature deaths. In the case of the Russian heat wave, resulted in 55,000 premature deaths. This is both a combination of the heat and the poor air quality during these events, particularly with regard to the Russian heat wave, in which many of the bogs surrounding Moscow caught on fire and the air quality degraded substantially. And so the key research question here is, has or will climate change increase atmospheric blocking frequency and or duration moving forward? And so this is an area of active research. There's not necessarily a conclusion on this yet, but many people are studying this phenomenon, not necessarily from the air quality perspective, but from simply the meteorology perspective. In my own research, I've done a little bit with stagnation duration change, and so I've broken this up by region. These correspond to the black boxes that were on the previous stagnation plot. But if we look at this plot, we're looking at the number of days per event and the distribution that we're seeing here. So 95th being the extreme long end of the distribution. And we can see in a few regions, the late 20th century being blue and the late 21st century being red, we can see in a few regions, the Western US, Mexico, and India, all indicate lengthening of the extreme duration of these stagnation events. And the longer these stagnation events last, the more time they have to accumulate harmful pollutants. Okay, so in summary, air quality and climate change linkages are diverse and complicated and can vary by season and region. Some meteorological changes are projected to exacerbate poor air quality challenges, and health impacts. And the positive and negative collateral benefits of mitigations exist, but it's active research. And finally, climate change is likely to alter the level of pollutant management required to meet future air quality targets, and that's through the avenue of changing meteorology. Thank you.
Hello, everyone. So my name is Seth Shonkoff, and it's good to be here. Just out of interest, I'm interested to hear where people are coming from. Who here is a student? Who here is not a student? And of the students, who here is in a school of public health? And who here is who studies environmental science? International affairs? Okay, great. So we will all learn a little bit of something. So I'm going to be sort of dovetailing a little bit on what Dan just spoke about, but I'm going to be talking about the climate change mitigation side. So what we're doing in terms of reducing emissions of greenhouse pollutants and what that might mean for air quality and subsequently for public health. So just to let you know where I come from, I'm the executive director of PSE Healthy Energy. It's an energy science and policy institute. We're in Oakland, California, Ithaca, New York, and New York City. And we function a lot like an academic university shop. We identify policy relevant data gaps and fill them. But then we step a little bit outside of the academic realm and put a lot of emphasis on translation of science and dissemination of science to ensure that it gets into the places where it's used to ensure more responsible policy development around our energy choices. So I'm going to first talk about some terms. We're just going to get some terms out of the way. And then I'm going to talk about the sort of two major climate change mitigation realms where we think about co-benefits. And then I'm going to spend a little bit of time talking about some unfortunate competing benefits, meaning, well, we'll get there in a second. So first, co-benefits of climate change mitigation. It's basically if you implement a climate change mitigation measure, do we also realize air quality and subsequently potentially public health goals? That would be the co-benefit. And you can also do the flip of that. Can air pollution abatement strategies double as climate change mitigation co-benefits? This is the unfortunate definition that we run into periodically in this space, or maybe even more than periodically. Competing benefits are policies that might cool the climate, but in turn are also increasing concentrations of atmospheric pollutants that are damaging to health. And you can also do the converse of that as well. So just to sort of call it out from the very beginning, climate change is a global issue. It's a global phenomenon. And when we think about, and when climate change practitioners and policy makers are out there talking about climate and what is driving it, oftentimes it's being talked about at a global scale. A puff of CO2 coming out of downtown Los Angeles means, from a climate perspective, the same thing as a puff of CO2 coming out of somewhere with low population density in the middle of a desert. And from a health perspective, place actually matters. So a puff of CO2 from a combustion source is often going to carry with it health-damaging air pollutants, which matters at the local and regional scale, and probably won't matter as much from a global climate perspective. So just keep that frame with you while we're walking through these slides. So in terms of the sort of one of the two main ways that we think about co-benefits of climate change mitigation from an air quality perspective is we think about co-pollutants. So pollutants that are emitted alongside, co-emitted with climate forcing constituents. A lot of what we tend to hear about are things like black carbon, VOCs, particulate matter, carbon monoxide. These are all products of incomplete combustion. Basically, if we're trying to mitigate climate change and we can reduce output of CO2, for example, we may also be reducing, but not always, be reducing some of these co-pollutants that are damaging to air quality and damaging to public health. A subset of these co-pollutants are, sometimes referred to as super pollutants. There's a super pollutant bill running through California right now. These super pollutants are co-pollutants of greenhouse gases that are also climate forcing. Black carbon and methane are getting a lot of play right now in the policy spheres, as they probably should for a variety of reasons, and some would argue shouldn't. Black carbon is the black constituent of particulate matter. Diesel emissions, for example, have a very high ratio of black carbon to organic carbon being the fraction of particulates that are light in color and are thus climate cooling because they beam energy back to space out of the Earth. And black carbon is the data is still emerging, but black carbon is thought to be at least as health damaging, if not more health damaging, than undifferentiated particulate matter. Methane is a strong greenhouse pollutant, less strong than black carbon on the short time frame, but it's long-lived enough to be globally mixed. And that ability for it to become globally mixed is something that contributes to global background production of tropospheric ozone. And ozone is also a climate-forcing pollutant, and it's also a strong respiratory irritant associated with premature mortality, exacerbation of asthma, etc. And then fluorinated gases are a super pollutant from a climate perspective. Very high global warming potential, very climate forcing, but do not necessarily degrade air quality. So these first two, black carbon and methane, from a super pollutant perspective, are pollutants that you could expect to see a climate and health benefit, and mitigation of F gases are something that you would just see a climate benefit from. So in terms of competing benefits, This is a very interesting space, and again, from a health and a climate perspective, sort of an unfortunate space. Sulfate particles predominantly are formed because of emissions of sulfur dioxide, which atmospherically transform to sulfate. Sulfate particles are light in color. They have a high albedo, which means that they tend to cool the climate, as opposed to things like black carbon, which are black and absorb heat and store it for their lifetime in the atmosphere. Now, emissions of sulfate particles are things that are the targets of, say, the acid rain program. Taking coal offline, putting in scrubbers to scrub out SO2 emissions. All these things are good for health. They're good for air quality. They are, in the case of, well, sulfur contributes to acidification of freshwater ecosystems. All those things are really good to abate, but when you pull sulfur out of the air, you're unmasking a certain amount of warming that's kept in check, at least on the short term, and that's something to take into consideration. The swapping of diesel in for gasoline. So diesel combustion in the mobile sector is associated with higher efficiency. You get more miles per gallon on a diesel engine than you can, all else being equal, on a gasoline-powered engine. That said, and so that's hypothetically good for the climate, assuming people don't decide to drive more if they have a diesel-powered vehicle. That said, diesel is associated with emissions of more particulate matter, especially diesel particulate matter, than gasoline. So there is an air quality and a health trade-off with moving a fleet from gasoline to diesel, but you're also losing on your CO2 emissions there. And from an air quality and especially a health context, the context of emission sources really matters. Again, if you have a puff of CO2 that goes into the air in somebody's home from burning solid fuels, from a climate perspective, it doesn't matter if it's inside someone's home burning solid fuels or if it's outdoors burning solid fuels. That's not the case for concentration of health-damaging air pollutants, and it's not the case for exposure and potentially for subsequent health concerns associated with that. So that's all I'm going to say, and that did not come out right, but there's my email. If you guys want to get in touch. Thank you.
So I'll just ask a few questions to engage these different kind of entry points on this issue. And one of them is, are these concerns about climate change and air quality, I mean, my perception is they have different places in our history, at least in the US, the Clean Air Act being 1970s and climate being much more 1990s, 2000s. Are they measured on bases that are equal, whether it's in terms of measuring the problem or measuring the response in terms of morbidity, mortality, however we make these laws? What are the prospects or what needs to happen in order to assume a way that we could just combine these issues? What would have to happen in a policy perspective to be able to combine and take into account air quality and climate change, under the same, auspices?
Yeah, go ahead.
Well, I think that's a big question. I think there's an institutional answer, or there's an institutional way of trying to answer that question, and then there's there's a reporting issue, an inventory issue as well. The institutional path is, this is not the only realm that this happens, but we operate in silos. With the exception of the Air Resources Board in California, which manages AB 32, which is probably the largest climate change mitigation portfolio in the United States, and they simultaneously manage air quality at the state level. With the exception of that, there aren't a whole lot of examples of where air quality and climate mitigation are under the same roof, driven by the same people, or at least people down the hall from each other. From an institutional perspective, getting people together and integrating it from the beginning, I think, is really important. From a reporting and even being able to measure where we're at perspective, this is a hot debate right now in the literature, but comparing everything to CO2 is something, and CO2 equivalence is something that is masking our ability to assess sustainable development and air quality goals alongside climate. And at the very least, if we are going to be moving in directions of trying to abate air quality issues and mitigate climate change simultaneously, we need to know actually what's being reduced. Are we reducing black carbon? Are we reducing methane? Are we reducing CO2? These are important because if we just report everything as CO2 equivalents, we learn something about climate, but we don't necessarily know anything about air quality and sustainable development.
Yeah, I think from a climate perspective, the focus on global average temperature change has really driven so much of the motivation behind the studies, and limiting that to 2 degrees as the be-all, end-all goal is perhaps problematic, but I think it's got baked into that and not necessarily discussed as much as the impacts that come along with 2 degrees change. And so on the air quality side, you're talking about mortality or premature mortality or morbidity, and that seems very highly impactful because people dying is something that gets attention. But the 2 degrees C, if you could attach to that the mortality that's associated with that, the climate, the impacts, the increase in extreme events, changes to air quality, all the other impacts of climate change, changes in agriculture, so on and so forth. I think it's more of a long-term perspective in terms of what's the most important thing.
And I mean, you raised the 2 degree, which is interesting. So if we talk about climate sensitivities, there are very different realities for 5 degree or 6 degree warming. And I'm just curious where you think the state of the research is at, or what's hampering the state of the research to evaluate what these, beyond any relative equilibrium, what this means to air quality and to, the measures of public health that will come out of climate change if we are to accelerate climate change. Does this, all of a sudden get a lot different and worse? Do we have any clue?
I would say the state of the research in terms of air quality with regard to, say, 6 degrees C change is, in my experience, it doesn't exist. We don't necessarily talk about horizons like that. If we're talking about the 2100 horizon, which from a publishing perspective, when you publish on the year 2100 and it has something to do with public policy or health, no one cares. 2100 is a really long time away. And so if you're talking about warming and getting to 6 degrees, there's not a lot of projections that say we're going to hit 6 degrees by 2100, and so there's not a lot of studies that necessarily try to tackle the air quality problem at a 6 degree level.
Yeah, I agree with that. I think the data is very thin when you start getting beyond 2-3 degrees. And in terms of, dropping that into the air quality climate change mitigation lens, I think it should create some pause. What do we need to be sure where we're going, right? And sometimes it takes time. Oftentimes, all the time, it takes a lot of time to flesh out the data, to understand the pathways that we may need to take. And if we don't have that time, then we're just going to be flying blind into a post-2 degree world, assuming that we go there. So some would argue that while CO2 is the most important greenhouse pollutant to be reducing emissions of, because ultimately that's going to be what's going to load the climate system into perpetually bringing us into a warmer and warmer world, we should be simultaneously working really hard on the shorter-lived greenhouse pollutants to buy ourselves time for adaptation and buy ourselves time for research into how we can adapt or how we can pivot from a mitigation or an adaptation perspective.
And do you see, thinking a lot about perceptions about these issues, even designing this event with David, on air quality being seen as the local issue, to be contended with, by local policymakers and really seen and felt locally, versus climate change being the global issue, obviously. But as I thought about it more, it's really what would happen, and I don't know if you've seen any evidence of this in each of your fields or in conversations that are happening, where air quality is started to be viewed as historically folks had recognized with air transport. China's air pollution comes to California. It's really a much bigger field than just a local issue, whereas climate change, which is thought of as such a big, broad, diffuse issue that's hard for people to grasp, is certainly something when it comes to sea level rise that's being discussed more and more, or even local air pollution, perturbation, that it becomes more local. And I'm wondering if there's a conversation that could happen, or if you're seeing it at all, where by mixing these issues up a little bit and kind of going in those different directions, that's an easier way to start to tie them together.
Yeah, I like the idea. I haven't necessarily seen evidence of that in the research.
I also like the idea. There's absolutely sort of international and trans-Pacific transport of things like particulate matter, black carbon, things like that. Ozone. Those, of course. Those things are pretty well established. I think it's worth a shot. I think it's also, I like that perspective, also because it would force each of these two camps, the climate camp and the air pollution camp, to really sort of reconcile and get really serious about what they're actually talking about and at what scale is important. Because impacts, what a population feels in terms of impacts from either climate change or air pollution or some integration of both of those is always local, but the drivers can be at different scales. So
So what are the priorities moving forward? I mean, I think of this, what you've been talking about. There's the technical aspect, stuff you've talked about, short-lived climate forces, super pollutants, the fact that the air quality pushes on the climate pushes on the air quality. We've talked a little bit about maybe not having coordination in a regulatory sense of these things. So is the priority more administrative, or is the priority more, partnerships, public-private partnerships? The locality, the local nature of these issues make them very close to the people, which is in the public realm. So is that something that, to avoid things like what happened with the diesel scandal, is that something that's a priority? Where do you see the best way to make headway here? They do seem like they're very separate issues with different histories, and wondering what you think priorities should be. Maybe it's even far greater research or integrated research.
Yeah, I think from the climate side of things, there's certainly a priority to increase our confidence in some of our projections. It's hard to make the link between increasing CO2 and poor air quality when we have such low confidence in so many of the meteorological factors that actually influence air quality. And so bringing up these themes are similar to the climate change discussion in general in terms of what can we improve on. We can improve on how we simulate precipitation in the models. We can improve on our resolution in the models, so on and so forth. And so I think there's a lot of overlaps there just in figuring out the meteorology and the impacts on the meteorology before we tie it into the air quality side of things.
I agree with that, and so I agree with that. So I'll focus a little bit on the community and the regulatory innovation inside. So first of all, I think it's pretty clear that we as a global population and engaging with international governance talks over what to do here around climate, we've been in gridlock for a long time. We have little pockets of things that are moving. They have their problems, but they're moving. AB 32, RGGI. We have the Paris climate talks, which were bigger breakthroughs than COPs in the recent past. But the fact of the matter is I think we need to, regulation and policy doesn't move unless people push it to move. It's just the way it is. If no one's asking for things to move, if no one's getting, pushing their officials and their staff and their electeds to move, it's not going to happen. So what is the frame through which people are going to be asking for climate mitigation to move? And I would argue that it's probably, in some cases, it's going to be climate in and of itself. In other cases, it's going to be sort of ancillary benefits of what it means to mitigate climate change from air quality perspectives, from sustainable development perspectives, transforming our cities to be, more walkable, et cetera. So I think that, that sort of interpenetrates movement building and getting better regulations that are more sort of speaking to these issues, paying attention to some of the things that Dan and I talked about with respect to, potential pitfalls. Not every climate mitigation is good for public health. Not every air quality and atmospheric health strategy is good for climate. So really educating up regulators while at the same time, engaging people with where they're at and getting them to engage their regulatory communities.
So one last question as maybe a bridge to the next panel, and then at the end of both, we'll have a really good discussion to tie this all together. So, it relates a little bit to what's going on with our metro and our economy, but there's a big push for infrastructure, both in this country, in Europe, and beyond. And I've been thinking a little bit when I read what you guys both wrote, and even, Dan, when you were speaking about, locality, stagnation, places, the placement of things. Infrastructure lasts a long time. Most infrastructure lasts 50, 70 years. So I'm just wondering, in the citing of stationary sources, whether it's here or India, growing, by leaps and bounds, in China, whether it's worth thinking about strategic placement in a much broader way when it comes to air quality transport, stagnation, just interactions between these pollutants, and whether that should be a much more thoughtful 21st century infrastructure, not just building good things that we know don't put out pollutants, but even when you have to build things that put out pollutants, being very strategic about where you site them and how you control them.
So from a meteorological perspective, if possible, if you could not build something that emits pollutants in the LA basin, I think that would be great. But the reality of, let's say it's a power generation station, putting it on the other side of the Sierra might be challenging to get the power over, that kind of thing. And so I think there's a bit of a disconnect there in terms of, maybe if it's not, in terms of stationary, if it's not necessarily power generation, which it's nice to have locally, maybe if it's manufacturing or something like that, something that's better to put, that's you're capable of putting further away. I think that perspective might work. I'm not sure that a decision maker would necessarily feel confident in some of the meteorological projections, so confident that they would not they would not site a stationary facility in a particular place. I think quite a bit more research would need to be done to build that confidence. But I like the idea of it. And if you if you look at the plot that I put up there of just air stagnation, the entire continent of India was red, and so it would be challenging to put a place to put a stationary source somewhere that's not going to increase.
So we have a paper that's coming out in the journal Energy Policy, and it looks at dispatching different types of energy based on air quality signals. So if the air quality is projected to be very bad on a given day or week, you could maybe with some innovation on the grid, you could dispatch cleaner fuels, more renewables, maybe discharge some of your energy storage if you have any on the grid. Increasingly, we will during the times when air quality is the worst or temperature is the highest, and that's a model that I'm hoping to get a little bit more play soon. What Dan is talking about in terms of would it be better for meteorologically speaking, and in terms of air quality and population level exposures, to put a fossil, if you have to put another fossil generating facility, let's try to not do that anymore, but if you have to put another one in the LA basin or for the LA population, if you could just send it over on the other side of the Sierras, that would be nice, but from a population health perspective, but maybe not from an ecological perspective. And so there's a lot of risk shifting, not just facility and geographic shifting. There's risk shifting involved in the decisions we make. So I guess I would encourage a lot of different fields, practitioners, academics, policymakers from different fields getting together to make sure that we don't have unintended consequences from what we do.
No, those are great points to end on. The idea of how to balance these risks, I think, is exactly this air quality climate change nexus, and avoiding the unintended consequences. So I think you said the two key words at the end. Well, thank you very much. I think we're ready for our second panel.
Spilled tea all over the stage. Happens, don't worry. Don't worry, we'll get it after a second. No worries. Please, please.
You all looked up.
Wonderful. Well, it's a lot of food for thought, and it's a lot of good scientific foundation to have. Before we discuss the way that we tackle these grand challenges, not only today with immediate policy measures, but also making the investments in the research and development in the innovation ecosystems necessary to solve these for the long term. I would be remiss if I didn't take a small opportunity to also, before we introduce our distinguished panelists, to thank the staff that made this all possible. I'd like to thank in particular Florencia Franzini, who is the true driving force behind the Energy Climate Program here at Carnegie and its work. Also another member of our team, Corey Park, who was instrumental in putting this together, as well as the wonderful support staff here at Carnegie, and our junior fellow, Jeffrey Feldman. We're privileged to work with the absolute best staff of any think tank in Washington, D.C., and it makes us all look better as a result. Now, if I can introduce our very esteemed and distinguished guest speakers, we're very fortunate to have with us today Judy Greenwald, who serves as the Deputy Director for Climate, Environment, and Energy Efficiency in the Department of Energy's Office of Energy Policy and Systems Analysis. Thank you, Judy. And also Dr. Varun Rai, who's an Assistant Professor at the LBJ School of Public Affairs at the University of Texas in Austin, where he directs the Energy Systems Transformation Research Group and has a number of ongoing projects relating to innovation diffusion, innovation cooperation, tech transfer, electric vehicles, solar, you name it. We're going to, similarly to panel one, open up with a couple of brief presentations. Then I will launch into a Q&A with the panelists, and then we're going to open things up at the very end to a broader Q&A up here. We're going to have our original speakers come up, and we'll open things up to the audience, and we'll be able to have a fully integrated discussion. So I'd urge you, stick around to the end so we can get all of your questions in. So without further ado, Judy, could you please kick us off? Thank you.
Thanks for having me. Do you want me to use this mic or the one that's on me?
You can use either, as you prefer. I think both will work, but why don't just pull that down just for double insurance.
Of course, I've never in my life actually pulled a mic.
Hey, I got the same problem.
I think mine's
And then just that to go forward.
great. Okay, so talk about domestic U.S. and the energy innovation outlook. So this is the problem that we face. The 17 warmest years on record have all occurred in the last 18 years. Not sure how well you can see the Y and X-axis labels for this, but on the left it's called anomalies in degrees Celsius, and that means the difference from the average of this entire period. The entire period started in 1880, and the last one is 2015, I believe. And basically what's happened over this period is we're getting warmer. And of course, this is the problem that we face and that we're trying to fix or at least avoid getting worse on a global average basis. This is a map of what are called nationally determined contributions. These used to be called intended nationally determined contributions. So you may be familiar with the INDC acronym or language. Now we're at NDC phase because we've already agreed to the Paris Agreement. So we've now got 177 countries that have these NDCs. Everybody in dark red has an NDC, which is quite an accomplishment. And the ones in dark blue, which you may or may not see, there are about 17 of them. These have actually have taken the second step to join or ratify the agreement. So we're on our way. Once 55 countries or 55% and or 50, once 55 countries and 55% of global emissions have joined, then it will enter into force. These are some examples of people's NDCs. They vary a lot. This was kind of the point of the Paris Agreement, is that this was a bottom-up approach. People came to the table with what they were willing and able to do, and they're going to start doing it. It's different from the top-down approach that we had been trying for some time and was only partially successful. So, for example, Brazil is reducing greenhouse gas emissions by 37% below 2005 levels in 2025, and 43% below 2005 levels in 2030. We have other folks with different types of commitments, like the EU has at least 40% domestic reductions in greenhouse gas emissions by 2030 compared to 1990. So people have somewhat different forms of their agreements or their nationally determined contributions, different pace of change, and this is all fine. We're glad that everybody's committing. This is a slightly complicated chart to explain, but I commend it to you all. There's an article in Science magazine that appeared, I believe, in December, late last year, 2015, and it's a nice explanation if you can. It's an example of a picture being worth 1,000 words, although sometimes it takes 1,000 words to explain this picture. But it's a really good visual of what we think the INDCs, now NDCs, are going to get us. So the left-hand chart is emissions, and it's emission pathways over time. So it starts in 1990 on the left and goes to 2100. This is, I'm talking about the left-hand graph first. And these big dark lines are sort of the big examples of emission pathways. There's lots of little faded lines, which are lots of different emission pathways, because there's quite a number of these that you could try. So the top dark line is the IPCC AR baseline range. And this is really an example where we don't do any more policy, and that's what happens to emissions. The next big dark line down is the reference low policy case, and this is where there's some policy, but we don't do all that much, actually. Does this have a pointer? The right button. Where am I? Not sure it's pointing. Shake it. That's great. Oops, that's not what I wanted to do. Well, imagine that, I'm pointing. And then this middle line that says, perhaps you can see INDCs, that's a model of, or a modeled, we attempted to model that, or the authors did, of what would happen if everybody actually meets their NDCs, and that's that sort of middle dark line. And then the left, the bottom dark line is an example if everyone met their NDCs, but then increased their ambition over time at the pace that the most aggressive NDCs are increasing their ambition. That's that bottom dark line. And then below that are this family of lines, which I'll explain in a moment once I get to the right-hand graph. Then you look at the right-hand graph, and this is temperature probabilities. On the left side of the right-hand graph is 0, and the right is 100, so it's 0 to 100% probabilities. And dark gray means 1 to 1.5 degrees, and light gray means 1.5 to 2 degrees. So if you see any gray, that's a probability that will actually stay below 2 degrees. And then the sort of pale orange is 2 to 3 degrees. This is all Celsius. The medium orange is 3 to 4 degrees, and the dark orange is 4 degrees. So basically, when you look to the left and you match it to the right, you see at that very reference scenario, we have essentially no chance of getting to 2 degrees and a very high chance of being above 4 degrees. The next line down is a little bit of policy, and you do a little bit better, but still no chance of staying below 2 degrees. It's with the INDCs that we're actually now on the map with some gray, or on this graph with some gray. So there's a little bit of a chance that will, something less than 10%, but non-zero, that will actually get to 2 degrees. And then if you go to that bottom dark line, there's a pretty good chance that we'll stay below 2 degrees, about 30%. And then there's this family at the bottom of graphs, because there's lots of different ways to, or graph lines, that there's a lot of different ways to get there. that gives us a 50% chance of staying below 2 degrees. So you see, the NDCs have taken us quite some way compared to the reference scenario, so it's a huge accomplishment, but also there's quite a long way to go if we want to have a greater than 50% chance that we're going to stay below 2 degrees. Sorry this is complicated, but I think it's worth doing. And I do commend this article. It's only like a 2-page article in Science from December 2015. It's a nice explanation of where we are. Okay, this is at the same or in parallel or just before the Paris Agreement. We also have this Mission Innovation Agreement. And in this, 20 countries, 80% of global clean energy R&D, will seek to double their clean energy R&D funding over the next 5 years. And for the U.S., this means we're going to double our investment from $6.4 billion in FY 2016 to $12.8 billion in 2017. And this is in our, we proposed the first, actually to double by 2021, sorry. But we've proposed the first tranche of this, so the first $1 billion increase of 20%, if we can increase 20% per year each year for 5 years, we'll get there, is in our proposed budget for the administration for FY 2017, but it's up to Congress what they're going to do with that. And in parallel with the governmental effort, there's also something called the Breakthrough Energy Coalition, which is a group of investors led by Bill Gates who have committed that they're going to work hard to actually invest in these technologies that hopefully there'll be more of in the pipeline because of this increased federal investment. And they're going to work to put their money behind commercializing these technologies. So these are parallel and complementary efforts that will be quite important. This is a map of who's participating in Mission Innovation, and it's a pretty important group. It spans 5 continents. This is everybody in blue is a Mission Innovation member. It spans 5 continents, representing nearly 60% of the world's population, including the top 5 most populous countries in the world. We emit 2/3 of the world's total greenhouse gas emissions, and we represent about 70% of the global GDP and more than 80% of all government investment in clean energy R&D. So having this group of countries make this type of commitment is certainly globally significant. This next one is a little bit about our own goals. As you can hopefully see on this graph, we have in 2009 rather, President Obama set a goal to cut U.S. greenhouse gas emissions in the range of 17% below 2005 levels by 2020. And then in 2014, we set a new goal to cut greenhouse gas emissions 26 to 28% below 2005 levels in 2025. So this 26 to 28% below 2005 levels by 2025 is that right little range. And basically what we say is we'll make best efforts to get to 28%, but we've committed to the range. And then back a few years is where our 17% target was. The black line is historic, and that red line is kind of our potential line to get to the 2020 target of 17%, and we're pretty on track as these things go. In order to get on track to do 26 to 28%, though, we're going to have to go faster. We're going to have to decarbonize faster than we would need to for the 2017. So we have to put in some extra effort. As many of you know, we have this President's Climate Action Plan, and this came about in 2013, and it's got 3 pillars: cut carbon pollution in America, that's our big mitigation efforts; prepare the United States for the impacts of climate change, that's our resilience efforts; and lead international efforts to combat global climate change and prepare for its impacts. And that's been our role in the Paris Agreement and other actions. I'm going to dig in a little bit to the power sector since it's so important. And it's basically an interplay of technological advance, market shifts, and policy. And so it's a little bit hard to tease any of them out. If you look at the left-hand graph, this is on the y-axis is the share of net generation. And the top gray line is what's been happening to coal's share of generation. And the bottom line is what's been happening to gas's share of generation. And as you can see, coal has been declining and natural gas has been increasing as a percentage of our generation, and they're just about at the same at the moment. And I think gas is surpassing coal a bit this year. So what this is really a story of is cheap gas displacing coal. And a lot of that has its roots in the shale gas revolution, which in turn has its roots in U.S. and U.S. government and private sector R&D. mean, the shale gas revolution that we have didn't just happen by magic. There have been a lot of work on that, and that's now coming to fruition in the marketplace where gas is winning out. The right-hand side shows a little bit more about what's been happening with new capacity additions. The first pair of lines are wind. Wind was the biggest set of capacity additions in 2015. The top blue bar is 2015 additions. The next blue bar is 2014. So this is wind's increase in additions. They're now the biggest. That's a pretty significant increase from 2014 to 2015. Gas additions were still significant in 2015, but lower than 2014. So that's the top brown line versus the bottom one. And then the bottom of these pair of solar lines is that solar additions were pretty constant between 2014 and 2015, but the expectation is that in 2016, solar additions are going to go way out past the end of either of those brown or blue graphs to something like 9 gigawatts. So this is a story, again, of this interplay between policy, technology, advance, and market shifts, where we've got state renewable portfolio standards, the federal investment tax credit and production tax credit. We've had a lot of R&D in the public and private sector, and we've been successful at bringing down the costs of renewables so that they're competing. So it's this interplay between policy, technology, and markets that's been driving change in the power sector. This is a little bit about air quality. I've given air quality a bit of short shrift and dominated this conversation with climate, but hopefully this will at least spark some discussion. This is comparing what's happening in 2014 on the right to what happened in 1980 on the left. So what's been happening since from 1980 to 2014 as an index. These are percentages. They all meet at the beginning at 0, and then their percentage increases or decreases are shown on the graph over time. So by 2014, the top blue line is GDP. So GDP is up about 147%. VMT is the orange, and that's up about 97%. Purple is population, up about 47%. Energy consumption is red, which is about up 26%. CO2, the green, is up about 17%. And then aggregate emissions of criteria air pollutants is down 63%. So our biggest success story is in the air quality, in the traditional conventional air pollution emissions that drive air quality. And this has mostly been a success story of pollution control technology. But we have done better, if you compare it to GDP, in becoming less energy intensive and in basically having our CO2 emissions grow much less quickly than these other drivers. But air quality has been a huge success on really any metric. But on all of these, we are doing better compared to these other trends than you might think. I guess I'll just spend a little bit talking about U.S. actions, but I'll try to go quickly. This is a pie chart of U.S. emissions with some boxes about key policies that are acting to reduce them. So electric generation is that big dark blue slice, and that's about 30%. And we have a bunch of policies, the Clean Power Plan and building codes and a bunch of other things that are driving emissions down in that sector. Transportation is that purple slice. It's about 26% of our emissions, probably dominated in the policy that's helping that is fuel economy standards, but things like VMT slowing are having an important effect as well. On the green slice, that's industry, is about 21%. We have actions on HFC rules, on reducing methane from the oil and gas sector, et cetera. On agriculture, we have a little bit of activity on reducing methane emissions. We have an overarching interagency methane strategy, which I can talk about if people like. It affects several of the sectors. And then up on that blue slice is 12% from commercial and industrial, and that's, commercial and residential, and that's non-electric. All the electric, residential, and commercial come out in the power sector slice. And then we've got agriculture, about 9% of emissions. Digging slightly into the Clean Power Plan, I don't know how much you can see this graph, but basically those two high dots are historical emissions. And then the top brownish color is what would have happened to power sector emissions without the Clean Power Plan. And that gray line is what's going to happen to them under the Clean Power Plan. The Clean Power Plan, as many of you know, sets flexible and achievable standards to reduce power sector CO2 emissions by 32% from 2005 levels by 2030, cutting carbon pollution by 870 million tons compared to base case by 2030. As you all know, this is under a Supreme Court stay right now, but the administration is confident that ultimately we will get through the courts and this rule will prevail. I'll spend just a moment on this, can get into it more in Q&A if people are interested. We have a natural gas modernization initiative that's part of our interagency methane strategy, but it also has other purposes. Reducing leaks from the natural gas system helps you on methane because natural gas is mostly methane, but it also helps on safety issues and it helps to not waste gas because if you're leaking natural gas from the system, you're wasting money and you're wasting energy. So there's multiple reasons why we're pursuing this modernization initiative. We have a lot of work going on across the department. ARPA-E is doing work on improving the technology for sensing methane. FERC is making it easier for folks to get cost recovery for investments in modernizing the natural gas system. We have a partnership with the National Association of Regulated Utility Commissioners to help them to reduce leakage. We also have a clearinghouse to help stakeholders as well as policymakers on this. And we are engaging pretty deeply with stakeholders on this and providing technical assistance to EPA in their voluntary programs. And that's all I've got.
Thank you very much. And Varun, would you like to continue the outlook a bit with a few of your own applied case studies and also give us a sense of where this fits into the international context?
Sure. First of all, thank you so much, Debbie, for having me here. This has been a very insightful discussion so far, and I'm going to steer a little bit in a different direction and talk about energy innovation, different aspects of energy innovation and how it is happening at a high level, but still with some more detailed insights here in the US, but also in other countries like China and India. What I'm going to do is actually first touch upon these four major debates that happen in the energy innovation sphere. What to focus on, energy innovation versus diffusion, which one should be emphasized more. The second one is who will fund energy innovation. There's so much out there, so much that we have to invest and do and discover and then commercialize. How are we going to do that? There is role for government, VCs, but then what else? Is it enough? There's lots of questions. Third, are there more key energy innovations that are going to come from countries not like the US, but countries like India, China, Brazil, and so on? If so, why and what does it all mean for energy innovation? And then finally, this is a question. When you're funding energy innovation, governments at all levels, local, regional, national, they're always very interested in what's in it for their constituents. Are there comparative advantages? Can there be benefits of commercializing, but then also supplying other players, other actors, other countries with these technologies, right? So when does that happen? Can funding energy innovation, does it mean that those firms who fund it or those governments who fund it, can they appropriate the benefits and then supply others, or does it just, go out there and everyone else can benefit? So these are all I think very important questions, not the universe of questions, and I don't claim to have answers to all of them, but I will touch upon each of them and share with you insights from my own work and that of my other colleagues in this broad area of energy innovation, innovation economics, and then hopefully that will generate some useful discussion. So, let's begin with the question of innovation versus diffusion, and there is a very important point about rapid decarbonization. You saw a chart that Judy showed where to have greater than 50% chance of being in the 2 degree C range, you saw those light blue curves that were coming down rapidly with emissions peaking in about a decade or so. That means we have to be deploying low carbon technologies, zero carbon technologies, potentially negative carbon technologies very rapidly. So diffusion is going to be very important. But at the same time, we do not want to lose sight of the innovation piece of it. It's very important. And here are many reasons, but two important reasons. First, the cost of mitigating and deploying these technologies without significant innovation is going to be significantly higher. There are all sorts of estimates, and one estimate suggests that without significant innovations over the next few decades, we'll incur about $20 trillion more in expenses in the long run in mitigating and staying in that zone. So it's going to be super important. Second piece here is that the types of innovations that are going to be important will come from a range of different directions, and we don't know ex ante what those are going to be. So we have to be experimenting along the way. We have to be working with different types of technologies, different players, different variations, and so on and so forth. And that's where innovation really comes into play. Before we necessarily deploy everything that we have today at rapid scale, which has its own issues in terms of how much can you learn. Too fast can lead to a lot of other problems, as we have seen in the history of energy. So trying to learn early on with different variations also brings innovation again back to the center. And then finally, we are talking about a very, very important problem, perhaps the most important that our generation has faced, perhaps the next generation will face, climate and air quality issues. At the same time, these are not the only issues that we'll have. Right, and we need to be thinking of keeping the energy system flexible with technological options, not just to deal with what we have today, but then also what we might encounter tomorrow, partly if we end up deploying things that we have today too fast, right? We don't know what problems we'll anticipate. And there again, innovation, I'll remind, this is resilience at the core. You have to keep that innovative dynamic flexibility in the system. So innovation, again, becomes very important. Moving to the second question on who will fund energy innovation. So I'll talk briefly about the role of venture capital and other players, and then a few comments on the role of government. VCs, as many of us know, has had a very checkered history here in the US of funding innovation in clean energy technologies. There's a lot of investment in the late 2000s, but then that receded. There has been a little bit of uptick more recently, but again, generally, it's been a very relatively negative experience of the VCs in the clean energy technology sector. In our own research, we have found that that should not be extrapolated too far, in the sense it should not sound as the death bell or death knell for VC's role in this industry. It's not that there is no appetite. It's not that there is no capital. In fact, there's a lot of capital out there that can play in. The real reasons are technological scaling involves a lot of risks, which are not necessarily well mitigated. There are issues and there are systemic reasons. I'll come to that when I talk about the role of government. So technological risk, market risk, and in some cases, regulatory risk, which are some of the key bottlenecks. It's not capital. Not to say that capital intensity is not important, well, it is. But then it has to be looked into the context of what some of the other underlying risks are. So the main point here is that there is a lot of appetite, and it wouldn't be surprising if some basic issues are fixed, that the VCs can come in and again kind of help address part of the problem. They are not going to be able to tackle this problem all on their own, but certainly they can be important players. One very interesting thing that we found is the rise of corporate venture capital interest in this space. Corporate venture investment has become very strategic, and they have become more active in engaging in this space and funding technologies that help address this bigger problem, of course, through their own business commercial interests. I have a slide upcoming. I'll talk a little bit more. But then there are other actors we have to be thinking about. For example, sovereign wealth funds. These are folks with trillions of dollars, but more importantly, a very long time horizon of how they think about their money. Two things which are very important when you think about clean energy innovation, right? Long time horizons and a lot of capital. Doesn't mean they're ready to kind of come in and just change the space. There are institutional issues and so on. So there are a bunch of possibilities. Crowdfunding, it's beginning to show up in its head. Much of the story is to be written yet. Program-related initiatives and so on. So you're seeing the emergence not just of VCs, but then other alternatives in this space who can come in, and it's going to be a very interesting dynamic space. A few lower level basic issues, in particular on the regulatory side, need to be taken care of. So let me talk a little bit about this slide. You may not be able to read all of it, but all you need to focus really on is the left two charts. Group A is what we call the narrowly exposed corporates. So you can think of these as, for example, oil firms who have, one of their main outputs is petroleum product, but then that's used in transportation. And so far, that has not had a viable alternative. We are seeing the rise of electric vehicles, but generally, automobiles are mostly driven on gasoline, diesel, and so on. So that's what we're calling as narrowly focused. And then the right column, the group B, are these more broadly exposed corporates. You can think of these as the electric utilities, where you have the Nests of the world, the Googles of the world, the Solar Cities of the world, which are coming in from the opposite direction and impinging very, very directly on the core business of these corporates. And so what you're seeing here is the investments that these types of players have actually made in the US in Series A, B funding. So you see that the darker green on the left column, that's being made by the group B, so the utilities. So they are funding a lot more riskier technologies. Those are the earlier rounds of funding. The second chart is showing that the group B folks are the white column. That's non-core services. So this is outside of their core area. So now not only they're funding early, which is more risky, but then also funding more of non-core. Just tells you how exposed and how threatened this group actually feels, right? And so this is a landscape of the types of stakeholders you're seeing and where you're seeing them actually engage in the energy innovation system. This picture is going to be very dynamic. You also have the GEs of the world, the Siemens of the world, and they're all kind of starting to see that their own business is changing and that they need to kind of stay plugged right in the center of this innovation evolution that is happening. I'll come to that a little bit later. So let's talk for a moment about the role of government. And when I say that, I mean beyond research and development and also demonstration. I'll just very briefly mention that one of the most important things that is missing when it comes to energy innovation is regulatory signaling. A good counterexample here is biotech or pharma, where the FDA not only serves regulatory functions, but then also along the way, it clears as a firm, as a new innovation, clears different hurdles of clearance. And that's also a signal to investors that the technology is maturing and is starting to reach a level of confidence and lower risk that is ready for larger scales of investments. That is absolutely not the case in energy. There is no such regulatory signaling. This is one of the most important things which we found, which is not known as in the conventional literature on what the role of government is. Basic research, plugging that with applied research, also funding demonstration. These are all known, but then signaling the competence of a technology at various stages as it tries to scale up. That's something that VCs do, but it's not something that they have done very well. It's something in the areas where you look, things have been successful, that government has had a very significant role in also doing that. So I think there's a very important role there for the government to kind of come in and play. It's not easy, right? Because the energy space is very fragmented from federal to the state, and the local regional variations also make that type of signaling kind of hard. But again, I think that's one of the more important opportunities. And then second is, of course, creating stable demand. One of the difficult things with energy is it's hard to distinguish between clean electrons and dirty electrons. For the customers, they just receive electrons. What that means, so historically in other industries, if you can distinguish your product and you say, you have a better, more valuable product, for example, a better healthcare product or technology that sells. There is demand for that. It's very difficult to do that in the case of clean energy innovation, and because the externalities are heavily under priced. They're actually not priced at this point mostly, and so there again, that's a known very important space for the government to play to create and support demand in various ways. Obviously the most obvious is creating a price on carbon, but then there are a whole range of other ways. For example, standards and other types of support, subsidies, and related policy tools to do that. But why does that matter? It matters because then you encourage entry by new firms and by players who can help come in and disrupt the system. Otherwise, it's very hard for entrepreneurs and smaller firms and folks who think about very innovative solutions to think and see that they have a viable exit strategy. So that matters quite a bit. Let me pivot and talk a little bit about are more innovations going to come from countries like China and India, and what are some of the key differences in the innovation systems? I think I'll start by saying that we need to recognize that the conditions for energy innovation in countries like India and China are actually quite favorable. Why? Because the issues, as we saw in the first panel, are actually quite difficult, right? And these countries also recognize that, understand that, and so their incentives are quite aligned in terms of thinking about solutions, and which naturally mean being very open to energy innovation. But in terms of systemic ability to do that, China is much closer and is at this point much more capable in terms of trying to not only incorporate and bring in technology from elsewhere, as they have done very successfully so far, but then also indigenously create that energy innovation, as compared to India, where the innovation system is much more fractured. And that's something we can take up more in the Q&A. Let me just add a couple points on China. So over the last couple decades, China has systematically invested in technology clusters, done a lot of R&D investments, created very specialized program in different parts of the energy sector, and the system is still nowhere close to the innovation system we have here, but you're starting to see an emergence of a really top-class portion of that innovation system, which is a positive indicator. And international players, international businesses who operate in China recognize that, and as a result, they have started to do joint ventures with Chinese firms, because that's a very important market. What it means is indigenous innovation that these countries are trying to do also affords them a kind of leverage to then work collaboratively with international firms and then negotiate technology deals, which China has been using very strategically. One other point which is interesting is historically, when we think about technology transfer, we think that firms bring older generation technologies to developing countries or emerging markets. Well, that's actually not necessarily true, and here is why. In many cases, look, one of the most important conditions for energy innovation is demand. You have to have new and growing demand to be able to support energy innovation. And where is that demand? It's growing rapidly in these types of countries, in China and India, right? And in many cases, so for example, take carbon capture and storage, where you don't want to emit CO2 in the atmosphere. You want to capture that and maybe use it or put it underground. Well, to build those types of technologies, you need to be building coal plants. And we're not building any coal plants here, and Judy showed. It's not just not building, we're actually not using the ones that we have here. Well, how do you think about those technologies? Well, the only way you do that is by working in countries like China, where they are actually building these types of plants, and then see if one can build energy innovation into that, build different types of storage and capture technologies, and then learn from that, and then kind of diffuse that knowledge broadly. So that's a very key point is that these countries, when they attract technology, it's not the older generation technologies anymore. In fact, they are acting as the vibrant marketplace to support energy innovation, not just by their own companies, but also by international firms. A final point, David, I'm doing okay on time? Still have a few more minutes. On comparative advantage. Does energy innovation accord comparative advantage, and when? And what is important is a very specialized type of tacit knowledge or localized learning where, so for example, Silicon Valley, Bay Area, right? Why has it been so successful in innovation in semiconductors and software? And you look around and Google's whatnot. A lot of it seems to be coming from there. What gives a place like Silicon Valley that advantage? And in the economics of innovation literature, it's one of the key components is tacit knowledge. Right? Folks being there and creating a system over time with networks of actors interacting with each other becomes very very important. Right? And when you think about similar thing happening in energy innovation, demand-side technologies or consumer-facing technologies offer that type of a possibility where a state, a region can actually induce that type of tacit knowledge formation, leading potentially to comparative advantage. I'll give you more specific examples just in a second. Why does that happen? It happens because when you have demand-side technologies or consumer-facing technologies, there is learning by use. So there is potential for customers to kind of use these technologies and provide feedback to the suppliers that then feeds back into the product development chain. That becomes a very critical source of innovation. Oftentimes, local factors like local climate, building infrastructure, building codes, regulations, complementary industry, these also kind of feed into this type of customer-facing energy technologies. Think about things one could do for home energy management system or solar or electric vehicles. So these are all the types of technologies which are quite propitious for tacit localized learning. And I'll show you just in a second some examples from my own research. And before I do that, let me mention that this type of knowledge is super interesting because they don't necessarily spill over very easily. And why is that important? Because one of the things that undermines a lot of significant investment in innovation is the fear that you innovate and then others can easily copy, and then you're not able to appropriate your investments in innovation. When knowledge is tacit and when knowledge is localized, it's very hard for others to kind of copy you, right? Because they did not operate in the same environment, the same local environment, which was the main driver for you to create those types of innovations. All right, so it matters for policy. If California, for example, sets out California Solar Initiatives, gives out $2 billion to firms to invest in solar technologies and install solar, the innovation that it generates is mostly local, mostly in California. We have compiled and did that analysis, and it's actually quite true, and that's super interesting because now the danger of that investment having been made and some other players, either other states in the US or actually other countries, taking away that benefit and then bringing on a lot of that technology to serve that market actually goes away, and a lot of that knowledge actually benefits the local economies. So let me just end with a few slides on some research we've done on solar photovoltaic balance of systems. So balance of systems is everything but the panels. So all the wiring, the inverters, site monitoring, site assessment, and whatnot, right? These today actually form 80% of the installed costs. Only 20% is cost of the panel because panel prices have come down very, very significantly. These balance of system is also has a very direct local tie. You can manufacture the panels anywhere, but then when you're actually installing, you have to pay attention to preferences of local customers, pay attention to local regulations and standards and labor laws and whatnot. So, right, there is a very direct local tie here. We looked at all the patents and patent applications filed in the US PTO from 97 to 2012, and we found that over 1,000 such applications directly on PV balance of systems, over 700 of which were filed by US companies. Only 30% of it was filed by foreign companies. We did a range of other analysis. I'm happy to talk about it in Q&A. But overall, what we found that 70% of these innovations were directly a result of US demand pull policies, in particular, the California Solar Initiative and the federal tax incentives. 30% came from elsewhere, and those were actually driven by the demand policies in their countries. What it means is the demand policies there incentivize innovation, and then they filed in the USPTO later, right? So domestic demand being a very critical aspect here in terms of helping create a comparative advantage and benefiting the local economies. So, and then this is the last slide I have. We found something very similar in China. What you're seeing here are the different provinces in China. On the left, you're seeing those are the PV balance of systems filed in different provinces of China. So the red is higher frequency of filings. And on the right, you're seeing the installed capacity. So essentially the local demand pull policies. You're seeing a very, very strong correlation. We have done similar analysis in Germany, in Japan. You see the same story being true. So again, this goes back to localized knowledge, localized learning, tacit knowledge. And whenever you have consumer-facing or demand-side technologies, that does provide those opportunities for localized learning and comparative advantages accruing to the local economies. Look forward to the discussions.
Thank you very much, Varun. Now let me ask just a few questions, and then I'll go off to the podium, and we'll bring everyone on stage and have a more open discussion. But I'm curious. I wanted to have a few follow-ups. And Judy, the interaction between mission innovation on the one hand, which is a collaboration between different countries, and the Breakthrough Energy Coalition, which is a coalition of different wealthy philanthropists, of different entities that goes beyond just the country level, and in some ways able to be more flexible and do different things. It strikes me that there's an enormous opportunity there if they can work together effectively and interface effectively. And I wonder, from your perspective as a practitioner, what's being done to ensure that these efforts, and surely they're the first of more to come, will not be duplicative, but will be complementary, and that the strengths that billionaires and philanthropists and wealthy individuals with experience in the private sector bring will be exploited in a way that's complementary to the assets that governments bring and the role that only they can play.
So it's a good question. So a few things. We are definitely talking to them. We have certain restrictions as the government about that we can't favor any particular private entity, but there are definitely discussions. We are mutually aware of each other's efforts. That was certainly true in the run-up to the announcement in December, that we both knew what each other were doing and recognized each other's strengths and weaknesses. It's going to be naturally complementary, in my view, just because of our respective roles and responsibilities and what we can and can't do. The government can do a lot in terms of the volume of investment we can make. We can be independent. We don't have to make money. We have a lot of institutional knowledge that we can use. We have a pretty vast enterprise, but we're also limited in what we can do in a lot of ways, and some of it's the same thing as our strengths. We can't make a lot of money, so we can't take as much risk in many ways with the taxpayers' money. I mean, there's some parts of the government like ARPA-E where we're more forgiving of letting them take risk, but a lot of the federal enterprise, it's really, you have to be pretty careful with the taxpayers' money, and failure is a problem. Whereas if you stand to earn a lot of money, you have a greater tolerance for failure, because as long as some part of your portfolio makes a lot of money, you can be willing to put more in. This, of course, depends on the size of the entity that's making the investment. So some of the venture capital folks have not been able to put as much capital in as they might have originally thought, because these investments turned out to be riskier. But the guys who are working with the Breakthrough Coalition are pretty big players and have a pretty big capacity doing it smart, but they have a pretty big capacity to have a relatively risky portfolio, and they're really better positioned than the government to take the innovations that come out of our earlier stage R&D, and that's a really important distinction I probably should have made up front, that the feds have a lot more freedom to do the very early stage R&D that doesn't actually have to result in a commercial application, and then it's the private sector that will take the fruits of that innovation and take it to commercialization. So I think that it's very naturally complementary, the two efforts, and we are communicating as much as is appropriate. And I think that together it's going to be quite a powerful force for innovation, both domestically and globally.
Thank you.
Then, David, if I can add a little bit, you can also ask the question from the perspective of some of the partners of the mission innovations. For example, what it means for a country like China or India. And there, I see both the issues and opportunities in the innovation system itself, which is not what an enterprise like the Breakthrough Institute would like to address. They would address more of the technology issues and then bringing that into the market directly and upfront. Doesn't mean that that would then be ready to diffuse in an energy system like India's, right? And which is where I think government's funding to activate its own both innovation capability, but then also transfer and recipient and innovation adaptation capability, so that once those technologies arrive, that can then diffuse within the system, and that requires a complementary set of activities and preparation, which is where I think some of the mission innovation resources or energy would potentially go.
That strikes in another question I had, which is, when we think about the differences in context between a country like the United States or a country like Germany and then countries like India or China, it strikes me that the sequencing of innovation priorities matters. So in India, for example, India's automotive sector is now adding more cars, the growth of auto sales in India is greater than China now. And there obviously would be a natural interest in having greater collaboration on innovation in electric vehicles and making sure that more of those vehicles are using fuels other than petroleum. But at the same time, India is still far from decarbonizing its power grid. So there's a risk that you are running electric vehicles off of coal power, for example, instead of petroleum fuels. This is a dynamic which obviously is, plays across a number of different areas. How do you think about the sequencing of innovation and driving with a technology focus versus a contextual focus of what are the needs? And this very much ties into the question of air quality as well. Do we want to prioritize technologies that have that lead with air quality and climate co-benefits together in countries where those air pollution concerns are most salient and most pressing?
So that's a hard question. Okay, so I think that different countries, different parts of the world have different situations that make certain things easier and certain things harder. So thinking about electric vehicles, the U.S. is actually relatively well positioned on electric vehicles in terms of both bringing them in because electricity is ubiquitous and also bringing them in cleanly because we are actually in the process of cleaning up our power sector. So I think that's an advantage that we have that maybe we'll be able to exploit. On the other hand, we have pretty cheap and abundant oil, and gasoline is a pretty tough competitor for any sort of new technology. I mean, gasoline's a really nice fuel. It's very energy dense, it's very easy to transport, it's ubiquitous, and so it's a tough competitor. So we have both the incumbent technologies here that you have to compete against, as well as a lot of advantages in terms of what might come in. An interesting case for me is thinking about hydrogen, which would be a very heavy lift in the US because we don't have a hydrogen infrastructure, whereas we do have an electric infrastructure and we have a gasoline infrastructure. So hydrogen would have a lot of trouble coming in. But some other countries where they don't have an already established gasoline and or electricity infrastructure, it might be easier to start from scratch with hydrogen. And there are a lot of people who actually think hydrogen's a pretty good fuel. for us to switch over to. It's hard that you're trying to switch from an incumbent to hydrogen, but if you've got not much infrastructure that you're starting with, it may be that a place like China could actually go hydrogen, and it would be just as easy as some other options. One other thing I would mention there is that, and then if China does that, then they could potentially get the learning, and then that technology could deploy elsewhere. So there's this interesting set of situations where different things might evolve, but then they might spill over to other countries. So it's a very interesting ecosystem of innovation.
I think the transportation sector in India offers a lot of opportunity. And this ties not only, for example, even with the dirty electricity supply that India has today, about 70% of it being generated from coal. If you were to deploy a lot of electric vehicles successfully, that will have a lot of huge local air pollution benefits, because potentially then you can push emissions from tailpipe emissions to centralized sources and then start tackling it there. So you can not that it will solve it, but it will resolve the problem better. Will give you more leverage in how you're dealing with that problem. So huge incentives from an air pollution perspective. India imports 90% of its oil, right? Here in this country, we talk about energy security, and we want to be energy independent. 90% oil imports, but that's not the problem. The problem is importing oil 5 years ago at cost of $100 per barrel meant India was spending a lot of high fraction of its foreign exchange on actually those. That has huge implications for trade internally. This has been a historic problem in India. So India does want to move away, right? And then third, as Judy showed on one of her slides, that 40% of India's cumulative electricity capacity by 2030 has to be from, according to their INDC, has to come from non-fossil based sources. That means a lot of solar, a lot of wind. Actually, there's a plan for 100 gigawatts of solar by 2022. Very, very, very aggressive targets. Not as much thinking, at least as of yet, in terms of what it means for integration. With the state of the grid that India has today, how would you even think about integrating that? I think electric vehicles have a very important role in potentially closing the loop on that. They can help stabilize the grid. They can take on extra power when it is there, or they can provide vehicle-to-grid services. These are a little bit far out, but then time to start, because the infrastructure has not been built, is actually today. So when you look at the incentives from India's perspective in thinking about changing the transportation sector, bringing more electric vehicles, I think the conditions are very strong. From the innovation perspective, though, again, you fall on this weak institutional setting, a fragmented structure, and a lack of coordination, as you have seen in the case of China. They have been able to move more or less in a coordinated fashion on a bunch of different things, but that's lacking in the case of India. I'll give the example of electric two-wheelers. So it has huge, so basically motorbikes and scooters and so on. It's a very high level of penetration in India, accounts for about 20% of emissions in the transportation sector. That's about 6-7% of total greenhouse gas emissions in India, right? China accounts for 96% of world's electric two-wheeler market. Almost all two-wheelers in China are electrified. India, almost 0%. It is again that lack of, and this is a very low-hanging fruit, right? But it's the lack of coordinated policy, but then also trying to adapt these technologies, thinking more systematically, building niches, build some projects, show some success, grow confidence in customers, and then start to replicate that. It's just been missing in some very, very obvious cases.
It should be noted that that Modi will be in town this week. It's a week in which
if you meet him please pass my message on.
Much of Washington D.C.'s eyes will be turned on India and on the bilateral relationship between the U.S. and India. Judy, from your vantage point, from your perspective within DOE, what has changed the most in recent years about the bilateral U.S.-India energy relationship, and what in your own work here domestically in the United States do you think is most ready to be shared and exported and scaled in developing countries and emerging markets like India?
So I think it's definitely gotten closer. I mean, there's a lot more technical cooperation. I'm pretty sure that the secretary is part of the meetings that are going on at the presidential level, but also at the cabinet level. And we have a lot of DOE folks go to India, and Indian scientists and government officials come here. So I'd say there's definitely a greater volume of cooperation over time. And I think India's stance within the UNFCCC negotiations has been more constructive recently. So it's been much more of a partnership, I would say, over the past few years. But India's got a lot of challenges, and I think the way we can be most helpful is if we can recognize those and also try to find solutions on the climate front that help on their more immediate problems. Not everyone has the luxury of putting climate at the top of their agenda when they first have, serious air quality issues, electrification goals, and, you have to make sure that you're thinking about climate solutions in the context of meeting very immediate and, in some cases, dire needs. And I think we've become more sensitive on that, and I think India has become more constructively engaged on the global dimensions of their situation. It is interesting sort of comparing these different countries where, you think about China is thought about as, more efficient and being able to just make things happen a little bit more with the stroke of the pen, which of course has pros and cons depending what it is that you're trying to achieve. But certainly it's a lot easier for China to sort of say thou shalt than it is for either India or the United States. And that has both pros and cons. We in many ways have greater opportunity, I think India as well, for letting 100,000 flowers bloom, which I guess is a Chinese expression, but it applies perhaps more to other countries where you can try lots of different things, and then you might have more failures, but you also have more successes. They might be small, and then you can build on it. So it's kind of these different political systems, I think, also have a very strong effect on the type and path of innovation and can potentially learn from one another. And, if you make a lot of small investments and then some of them pan out, that has certain advantages. Certainly if you're able to make really big changes, that's exciting, but also you can make big mistakes. So I think that I wouldn't prefer any system in terms of its ability to innovate, but they are different and they could lead to different outcomes.
Very good. And before I open things up and have our other panelists join, I'd like to ask one final question, which is a bit more hypothetical and hopefully a bit more provocative as well, which is, in 5 or 10, 15 years from now, we're talking more at these roundtables and discussions about the concept of geoengineering. And if geoengineering, whatever the technology or the geoengineering approach is, if it is appearing to be more feasible or is even appearing to be imminent, not judging the desirability or making any normative judgment on geoengineering or that scenario, but I wonder if either of you have a perspective on how that would change the perceived cost and benefits of energy innovation. Both of you emphasize the importance of knowing that there's demand for whatever that major innovation is. And if you believe that one of the fundamental challenges of our society that will shape many policy frameworks to come, climate change, is one that could be dealt with perhaps at great risk, but also at significantly less cost than we think through a geoengineering approach, what does that do to our entire incentive system for long-term energy innovation? And what do you think we could do perhaps as as societal stakeholders to ensure that we still have the appropriate amount of innovation and that we don't allow the externality of suboptimal innovation to exacerbate in such a situation.
So there was a National Academy of Sciences study, I think it was a couple of years ago, getting at this question, you know, what approach should we take to thinking about geoengineering? And I think what they said is we need to start doing some research thinking about this, but stop short of any kind of experiments that might actually have potentially dire consequences themselves. I mean, the thing that about climate change is essentially we're doing geoengineering. We're putting man-made emissions into the atmosphere, and we're somewhat accidentally engineering the atmosphere in not a good way. So we could think about trying to make other compensating changes, but we could also screw that up too. So, and we could screw it up in quite a big way. So I think I agree with the National Academy of Sciences that we need to dig in on this and see what our options are and understand the implications, but be very careful. And also make sure that we're thinking about, you know, compared to what. I think that some of the geoengineering options that people might get excited about might actually look pretty bad compared to just reducing our emissions. So it really depends on what you think you can accomplish, what your costs of that are both to the environment and actually costs of doing it. I mean, a lot of these geoengineering options are actually quite expensive. So you have to sort of think about, okay, how much can we reduce emissions, how quickly, what does that really look like? And then if that is just infeasible, then we have to think about, well, what else can we do? And then think about what you might have to do on the back end. One area that I've been digging into, which I think is an important emerging issue, is capture and storage combined with biomass combustion, which is or gasification and using that energy. That's an interesting technology potentially. There isn't a lot of research on it, but it is a way in the out years to get negative emissions if you can't bring your emissions down quickly enough. But it also, we don't know that much about it. It also could be expensive. There are a lot of issues with using biomass because it competes with other things we might want to do with biomass. But it is an interesting example. It's not quite geoengineering, but it would be taking essentially CO2 out of the atmosphere and putting it underground that if you put too much in over time. So that's a technology when we explore these types of scenarios in models. If you have relatively low cost estimates for that, it starts to come in the out years, but we don't actually know much about what the cost and performance of those technologies would be. But it's an interesting way to think about what we might need to do in the out years if we can't decarbonize fast enough.
Any thoughts on that?
I think Judy did it up very well. Just very quickly echo some of her thoughts. We are accidentally geoengineering. So, in the first panel, we heard about the sulfates and the gray carbon that actually beam off heat back and actually lead to some cooling or mask global warming. So that's happening. We need to be, Judy also had a slide that showed probability distributions of potential temperature rises. And on many of those scenarios, you saw that there were active red bars, meaning greater than 4 degree rises had significant non-zero type probabilities. Those are the types of scenarios where we have to be open, at least in terms of research thinking for options, backstop options like geoengineering, but then also capture from biomass and storage, because those scenarios are so uncertain. We have very little both scientific as well as even worse understanding in terms of economic, ecological impacts of those scenarios. And I think that's where this type of some capability to think about what we might do as a society in those scenarios could be helpful. So we have to be open. Just final point, again, referring to Judy's Fawcett et al. 2015 slide, rapid need for decarbonization now, right? I don't think we're going to be ready from a geoengineering perspective in the next 10, 15, 20 years. All right, there's a lot of very basic thinking, and then potentially anything that gives us any real capability to do that. Much of the action actually needs to happen now and with the Paris agreements with the INDC and so on, we are on course. I think we'll hopefully see more real action on energy innovation, geoengineering or not.
Great. Thank you both very much. If I could ask you both to stay here and then have Dan and Seth come up and join us up here. Those of you with questions, you've been very patient to wait until now. Please just raise your hand and we'll go around. I'll collect them probably 2 or 3 at a time, and we'll try and get in a couple rounds of these questions. Yes, we've got a gentleman in the aisle right here, one next to him, and then also a question at the back. We'll take those 3 first.
Hi, my name is Chandler Sachs, and I'm an undergrad at Cornell studying environmental policy. So this is a question for the Deputy Director. So when we're addressing the confidence estimates in regards to scientific estimations about climate change, and due to the fact that politicians, whether it be in Senate subcommittees or state legislatures, use these low confidence estimates as ammunition against legislative action, do you see a way that academia can change its role in policymaking to address the nuances of climate science?
A great question. So I actually would be interested in your opinion on, I mean, the graph, that image that I showed from that Science magazine, I thought that was a really good way to talk about probabilities in a way that actually makes people understand why we're worried. But you're right, it's really true. It's actually not only possible but likely in the United States to go pretty far in your career without studying a lot of math. And I think that's a huge problem. And so we're always trying our best to explain quantitative concepts in a way that's useful to people who have to make decisions. But I think it's a challenge. I think we have to be honest about what we know and we don't know. I actually think people in their daily life make decisions thinking probabilistically, but they may not know it. And I think if you can use examples, I try to do that a lot. You know, if you're making a decision about whether to pass a car, right? You're sort of calculating how fast they're going, what your chances are that somebody else is going to come along while you're trying to pass. I mean, I really think people do probabilistic decision making all the time, but we have to help them, I guess, recognize that. So I think that the thing is to try to get better at explaining and also hearing people, because I think this is a problem too, is that I think this is a much broader political problem. We're having more trouble listening to each other than we used to really try to understand when somebody is disagreeing with you, you know, why? What is it that they don't understand? What is it they think they understand? What is it that maybe you don't understand? And so I think that there's really no solution to this other than really understanding where each other are coming from, what our principles are, and trying to do a better job educating.
There's another question over here.
I'm Chi Han from Xinhua News Agency. Thank you for panelists' wonderful discussions. My first question is for Judy. In your speech, you said that the higher court has suspended the Clean Power Plan in February, but you also said that you think that the court will support it finally. So my question is that, can you tell some detailed reasons why you are so optimistic that the higher court will support the Clean Coal Pipeline in its final rule? And my second question is for all the 4 panelists, is that what's your expectations for the new U.S. government after the general election toward the Clean Coal Power Plan and the Paris Agreement? Thank you.
So the reason that I'm confident is probably not so much a personal view as talking to the folks in the administration who are arguing the case. The way it works is that the Supreme Court has said that the rule is stayed. It can't go forward. But they didn't pass any judgment on the merits of the rule. They just said, while we're figuring this out, you know, don't move forward. So there's been no decision on the merits of the law, of the rule in terms of its legal merits. And so both sides have written briefs. You have, and most of that is in the public domain. And it's the judgment of a lot of the people that I respect within the administration that we have a very strong case and that we will ultimately prevail. So it's really a legal opinion that we have, and we'll see what the court says.
Right. There was a question back there.
Herbert Regenbogen, Touro Law Center.
I can't hear you.
We just speak directly
Thank you
into
very
it.
much.
Yeah.
Thank you very much. This discussion is about climate change or air pollution, but little has been said about public health. And as such, the air pollution also has an impact on water and soil as a total scientific concept of innovation to improve the environment. What I'm missing in all of this analysis, and comes back to Cameron Hepburn's approach, and a recent article by Dieter Helms in the Oxford Journal of International Economy, is the macroeconomics of analyzing climate change and its impact on economics. So that means that when we speak about the impact of climate change on the economy, we don't talk about replenishing the ecosystems. We don't go into the question of how the natural capital affects our GDP. And my question is to the Department of Energy. Why is this not being exercised?
We certainly try. Even the terminology is something we have to work on, because it's called cost-benefit analysis, right? And usually the costs are the compliance costs, and the benefits are what you get if you reduce greenhouse gas emissions. What are the climate benefits? And the categories of climate benefits are things like less heat waves, less drought, less vector-borne diseases. I mean, those are the benefits, and really we have this somewhat complex conversation about, well, what's a cost and what's a benefit, and how do you actually look at them evenly. Ideally, we would look at all of this in an integrated framework. We would think about every time we are spending money to reduce, or proposing to spend money to reduce greenhouse gas emissions, is that actually less than what's called the social cost of carbon, which tends to be a somewhat different enterprise? Are we actually, by investing or spending money to reduce greenhouse gas emissions, are you actually saving money, in a sense, because you're reducing the cost of climate change? So everybody, we all try to do this, but it's difficult. We're actually better at estimating compliance costs or the cost of new types of power systems than we are at estimating the cost of the damage to the environment done by climate change. I just read an article fairly recently that we're having a huge impact globally on where birds live, that birds are moving around from where they used to be native to other places because of the climate shift. It's very hard to say, well, what's the cost of that? What's the benefit of that? So you wind up, often you have the cost side of the ledger, which is what does it cost to change your energy system, against benefits that are, about human health or ecological health, and those are harder to quantify. We are doing a lot of work on this. The whole effort to generate a social cost of carbon has been based on this type of research, but it's difficult, and a lot of what we care about most deeply is hard to monetize.
Excellent. Let's take another round of questions. We're going to take them all together this time. So first at the back, then we'll take a gentleman right here, and finally a question right up front. Please identify yourself as well, actually, prior to your question.
I'm Yo-Yo from Hong Kong Phoenix TV, and my question is for Judy. On the US and China, and for other panels, US China are having the 8th strategic dialogues right now, and they also reached a lot of agreements and also understanding in the energy area. What do you see the areas of cooperation between US and China in the energy area in the future, and also the dynamics of the cooperation? do you see it's more private sector driven or it's more led by the two governments? Thank you.
There's a lot of cooperation. I'd actually say, I think I'd have to go back and look at calendars and dates, but I actually think the cooperation has actually potentially been longer and deeper than with India. I think the India cooperation has been more recent and is growing. So we as a country and often as private sector entities from the U.S. are doing a lot of collaboration with China. There's a lot of joint delegations that go over where it's a combination of government officials and private sector officials from the U.S. go over to China, talk about individual projects as well as broader programs and policies. Also vice versa, a lot of Chinese delegations come look at technological projects we have, talk to officials as well as private sector. There's been a lot of collaboration, for example, on carbon capture and storage. A number of projects in China. I know that some of our DOE folks have gone to see what's happening over there and vice versa. So I'd say the cooperation is actually quite broad, quite deep, and it's both public and private.
And I think a really positive element of the relationship as well. So even where there are differences on other issues, there are a lot of mutual compatibilities there. Yes, sir, a question from you. Please identify yourself as well, and then we'll go right up front.
My name is Evan Lewis. I'm with the Program for Public Consultation. I sort of was going to add to Judith's answer about the Supreme Court. I think the reason the administration is thinking very favorably about the outcome of anything is because there's been several Supreme Court cases that have given power to the EPA's ability to regulate carbon dioxide as a pollutant, and so they're going to build on this case as they move forward. My question is more related to something the gentleman over here mentioned, is that there's some new technologies, biogas digesters, that'll turn animal waste and converts the methane from animal waste into natural gas, which is cleaner burning and potentially competes with the natural gas coming from fracking. But animal waste also has an impact on water quality, and that's something that tends not to be discussed, is that some of these air effects, some of these air pollutant effects either rain down into the water supply or affect the water supply pretty directly, and yet there's not a whole lot of conversation about it.
Excellent. Thank you very much. And a question right up front here.
Hi, I'm Miao Li from with the International Fund for China's Environment, and thank you for the discussion about air pollution, this problem. Because we've been trying to promote U.S.-China environmental cooperation for 20 years, and recently we found some trend from 2015 to 2020, China is going to invest 1.5 trillion in environmental protection. So it's like a huge percentage is going to come from the private sector. So actually next June the 17th, we're going to hold our air pollution control summit in Washington, D.C. And we have brought a lot of Chinese companies from China. So they are coming here looking for technologies. But we found the problem is we haven't been able to find many American companies they are kind of interested. So any suggestions from any of you how to effectively approach American companies kind of to promote the cooperation between the private sector from the two countries? Thank you.
Okay. So a question on interactions between addressing climate and air pollution, and then the interaction effects with water. Either your own research or just research you're aware of in this field would be useful to highlight. And then a question on mutual commercial opportunities between China and the United States on air quality.
I'll just quickly make two comments. One on the first question on U.S.-China cooperation, and if most of it is led by private firms. I think the private folks, as Judy mentioned, are certainly heavily involved. But then also, if you look at the cooperation and some of the initial projects that have been started or are in the process of getting started, there is also a lot of pre-competitive joint collaboration looking longer term on the range of different types of technologies, biofuels, carbon capture and storage, and so on, which involve national labs on both sides, academia, academic folks on both sides. There is some very innovative thinking and arrangements about intellectual property sharing and then co-licensing and so on. Much of this is actually pre-competitive. So private and the corporate world is certainly involved and driving this to some extent, but then also you're seeing much broader public interest and public institutions being engaged directly. To your question on suggestions for involving American firms, I don't have a very specific suggestion. I don't work in that environment, but I would begin by generating or trumpeting this program to begin with. That sounds like a lot of resource, a lot of investment. Our firms here, our stakeholders here, generally aware, and here is why I say this. We wrote a paper a couple years ago looking at intellectual property regimes and how does that matter for low carbon technology transfer. And the reason we looked at that question is in global negotiations, one of the common long staying thorn has been countries like China and India saying, give us the technology, we don't have the technology, and then firms in the developed world who have actually invested a lot and generated that innovation saying, sorry, let's think about collaborative project and let's do business. So that's the rhetoric. The reality, and that's why we did the project, is you are seeing billions of dollars flowing every week, both sides, right? Lots of investments, lots of technology flowing, lots of very innovative business, commercial, long-term agreements being done by the biggest players on both sides. So when there's opportunity, when there's a market like China, firms get interested and do a lot of business and flow a lot of technology and funds. So I would begin by generating awareness that there is a big program, there is going to be big focused investment. This is a serious effort that involves very serious Chinese players. And then use leverage instead of going very bottom up. I would kind of create a top front and then leverage that then to communicate and leverage response from American firms.
Any other responses?
Well, I was going to just respond a little bit to the issue of oil and different energy resources. I think it's very true that we do, sometimes a good job, sometimes a bad job in assessing environmental impacts, but almost always silos when it comes to energy. That's starting to change a little bit, but we are seeing energy becoming an increasingly playing an increasingly important role in water and vice versa. The issue of oil and gas development enabled by hydraulic fracturing and other methods that was mentioned by the person asking the question. There's a lot of oil and gas being developed in pretty water scarce environments throughout the West. That is, from a water quantity perspective, is something that needs to be taken deeply into consideration. But also something that needs to be taken deeply into consideration is what these technologies and what this type of energy development is innovating in states like California, Wyoming, and Colorado. For example, a lot of oil and gas, there's a lot of conversations right now and some action in figuring out whether it's a good idea or a bad idea to be reusing wastewater, produced water from oil fields for things like agricultural irrigation. I was appointed to a panel, a scientific panel to look at this in California on the Central Valley Water Board. There's 2 water districts in California right now that reuse wastewater from oil fields. And the question is, what are the public health, food safety dimensions of this? And it's, I would love to talk with anyone who wants to talk about this more, but it's not clear. And there are more unknowns than knowns. And a lot of what we need to assess is, what are the chemical constituents that are used, and how do they play out with respect to crop uptake and food safety. So that's just one issue among a whole slew of issues that are going to be upon us and are already upon us for consideration by regulatory community as well as the court of public opinion. So just want to.
Yeah, excellent. Let's take one more round of questions. Yes, we've got one here, and then we'll actually grab the three that are back there, those three in the cluster right there. Then we'll see if we have any more time, but I think that'll probably be it.
Hi, I'm Levi Tilleman. I'm with the New America Foundation. And thank you, David, for putting together such a terrific panel. It was very informative. One thing that struck me, though, is there's so much discussion of China. And sort of pivoting off of the panelists' comments on silos, I think it might be very useful to have someone who's a specialist on Chinese politics. Because I think sometimes we think that in China you just sort of, with the stroke of a pen, can create a policy and things are successful. But it's actually extremely complicated to implement these policies in China. And they have their own political constituencies and interests that are at war when you're trying to implement new energy policies over there. So it seems to me that that might be a good area to explore future interdisciplinary studies.
Absolutely, and I think that actually strikes at a conversation we were having last night with the speakers. So we were discussing the relative maturity of our understanding the political economy of innovation and of energy transitions in China and India. I mean, China, you're making a comment on it, and I think we understand actually even less about India sometimes, and the degree to which there are a number of complexities and nonlinearities in the political economy of energy in India. So we can address that in 1 second, but let's grab the rest of these questions.
Okay, I have a question that's, I'm Peg Christoph at Stony Brook University, and my question relates also to a bit of geopolitics, really. Does the United States have relations, bilateral relations with countries in Southeast Asia? Or is this something that is more focused on China or India in this area of climate change?
Hi, I'm Ash Choudhury and a summer intern at the Simpson Center. So my question is about knowledge diffusion, as Professor Rai was talking a while back. That talking from an environmental perspective, it is perhaps best if we can open all the new innovation to everyone for use, rather than giving an exclusive right or IPR to the innovator. But from the other perspective, it is perhaps unfair to the innovators if we do not give them an exclusive right, because then there will be no incentive. So is there a way to strike a balance between these two? For example, Germany made a lot of improvement in solar technology, but I mean, when China started using those technologies, the German companies failed. They went bankrupt, many of them. So how to strike a balance between these things?
Abel Zakarian. I am an environmental epidemiologist by training and most recently worked as a volunteer in Kenya in areas affected by climate change and had the opportunity to see effects of both air quality consequences and water scarcity on health. So I'm interested in thoughts perhaps on what kind of infrastructure is needed to address the global public health consequences of climate change. What role might this play in designing interventions, whether it's policies or driving technology, or perhaps even reducing some of the uncertainty about the logic effects.
Thank you very much. So we've got questions on infrastructure and how we use it in a creative and constructive way to reduce some of those uncertainties, to address the certain impacts that we know we're going to have as well. We've got a question on integrating an understanding of political economy into this, so that we're not just thinking about this in the abstract, but we're thinking about the politics of environmental controls, the politics of environmental regulation. In China, for many years, state-owned oil companies were some of the major obstacles to creating more rigorous and implementing more rigorous fuel standards, for example, in the country. And I think that's oftentimes lost by audiences that aren't closely watching the Chinese context. We had a question as well about Southeast Asia cooperation, and then, of course, about intellectual property rights. So whoever has strong opinions on any of those is free to launch in.
I can take the IPR first, and then maybe others can join. I think you hit on a very central question. I mean, this is basically what patent organizations across the world try to do: strike this balance, right? You have to provide incentives for innovators to innovate and potentially benefit from that. Otherwise, why would smart folks do that? At the same time, you also want to make sure that you're not granting very broad rights. You are delineating and allowing and, in fact, encouraging related innovation or innovation around the boundaries, so that there is broad public benefit. So that's a very central question in intellectual property rights. To your specific question on how do we think of that in terms of energy innovation and clean energy technology innovation, the common objective of leaving the private folks in a market setting to do what they have to do, that shouldn't change, right? Whatever the broad settings and rules are of intellectual property, that stays. That said, given that the uncertainties involved in terms of what types of things to innovate in, what types of technologies will actually mature, scale up, commercialize, and potentially bring money, the long time horizons that we talked about, right? Not software, which you can invest in and find out what happens in a year or two. We're talking about 10, 15, 20 years, right? A bunch of these things makes public investment, government investment in energy innovation even more important. And when that happens, then what you can imagine and what needs to be done, is being done in certain quarters, is requiring those investments and innovations coming out of those investments to have less of corralled intellectual property for only certain players, all right? More broader licensing rights, more broader and proactive knowledge sharing, and so on and so forth. And that's kind of built into some of the collaborative efforts like the U.S.-China Energy Collaborative and so on. You're seeing similar efforts wherever government is starting to build funds to fund these types of technologies. So, and I think with more public involvement, you are going to have that effect indirectly, but not in the main system. I don't think the main system, or tweaking the main system just for this is not the right way to go about it.
On the public health and infectious disease side of things, I think that in the climate sciences we often dwell on. I lost my train of thought. We often dwell, and much of the discussion today has been on the idea of mitigation. And in working in the field for a little while, I sometimes doubt the fact that we're actually going to mitigate. And so there's the reality that things may not be as rosy as these mitigation scenarios that we're painting. And so I feel that one of the responsibilities of a climate scientist, and particularly someone that studies impacts, is to actually is to look at what happens if we don't mitigate the carbon problem, and what would those impacts be? How can a society build resilience or adapt to that problem? And I think that's one of the key things for both public health and infectious disease. We were talking a bit about infectious disease last night, and just in there's so many difficulties with determining impacts. And then when you get to infectious disease, you bring in all these organisms. And biological organisms are incredibly difficult to predict. Just in thinking about malaria and temperatures, things like that. Mosquitoes bite more frequently when it gets warm. They become the disease becomes infected, becomes contagious quicker in their gut when it gets warm, but they die quicker when it gets warm. And so there's all these nonlinear relationships that we are still working on to assess the real impacts there.
Just to dovetail a little bit for the epidemiologist back there. So in terms of what types of infrastructure to invest in to, help places to adapt to warming temperatures and the very real impacts that are already starting to be seen and gaining momentum. It is totally variable across space, and it really matters. Are you near an ocean? Do you need to set up seawalls? Are you India with bright red colors of stagnation of air over it? And so, I think it's not a very straightforward question, but or there are no straightforward answers to that question. But it's certainly important to start that adaptation conversation now, yesterday, to figure out what various localities will need, and then it should be noted that a lot of the places that are thought or predicted to suffer the worst consequences of actual climate change impacts are a lot of these places have the least ability to pay for adaptation, and so that's a major thorn in the side of the mitigation conversation as well as the adaptation conversation, it sparks fly when that conversation comes up, but that's a conversation that's really integral to have and to come to conclusions about.
I'll just comment on that. I think this is your intent, but it's not an either or. Certainly the more we mitigate, the less we'll have to adapt. And certainly I think it matters. In fact, I know it matters. Even if you mitigate some, that's better than not mitigating. And if you mitigate a lot, that's even better. So I think it's important to think about doing the best we can in all of these arenas, and also making sure that we understand the implications in a probabilistic way, because a lot of times it is. This is about risk, and doing the best we can to mitigate our risks and to make the investments and make bets on things that we think have the greatest chance of helping us solve our problems. So I really do think that there's an enormous reason to be optimistic that we can do better, and there's also reason to be pessimistic, and that we just have to try to do the best we can to solve the problems that we have before us.
Yeah, I would say, just to put this all together, I think it's a mistake to pit adaptation against mitigation. But I think that both are important to take into consideration and to think through.
Absolutely. And very, very apt closing words. That's the point at which we'll unfortunately have to end. We obviously opened a lot of threads of discussion that we could pull, and perhaps some of you will have the chance to catch some of the speakers afterwards and ask some of the questions if you didn't get to here. Allow me to make just a brief plug for those of you who are interested in exploring other avenues of mitigation, other avenues of innovation that are going on in policy. We've got two very exciting events next week that we'd love to see you at. On June 14th, Tuesday, I'll be hosting an event here at Carnegie on autonomous vehicles, driverless cars, and specifically what they mean for energy and climate policy. Are they going to be obstacles, or are they going to be opportunities that we can leverage? Then the second one, the following day, Wednesday, will be an event led by my colleague Deborah Gordon on designing a smart carbon tax for the petroleum sector, and a discussion over what that would look like, painting a picture for what a smart carbon tax to come might look like in the petroleum sector. So please join us next Tuesday and Wednesday. Thank you very much for joining us today. Allow me to thank once more the wonderful staff here at Carnegie that made this event possible, and most significantly, let me also thank our wonderful distinguished panelists who led a wonderful discussion today. Thank you very much.